morning friends, already we discussed about the superposition principle, right? Now the superposition principle is that when the point of a medium comes under the influence of two or more waves, the net resultant displacement of a point is the vector sum of the displacement of individual waves, right? That means the resultant displacement y is equal to vector sum of displacement of individual waves, right? Now here we are going to derive the equation of the resultant displacement of or the resultant equation of progressive harmonic wave or the superposition of two progressive harmonic wave moving in x direction in straight string. For that purpose, we have now like this way consider the two progressive harmonic waves. Consider two progressive harmonic waves moves in positive x direction or the positive x axis, having same angular frequency, same angular wave vector, angular frequency omega, wave vector is k, wavelength lambda, and amplitude E. Amplitude E. But the initial phase difference, initial phase are different. My initial phase are different. Then we can assume that suppose the initial phase of wave, the displacement is represented as y1 xt is 0 and y2 xt has initial phase is 5. Here we consider the two waves represented by the displacement. One is the y1 xt having the phase is 0 and another wave having the displacement y2 xt has initial phase is 5. Therefore, the equation of progressive harmonic wave, equations of two progressive harmonic waves are, one is y1 is equal to a sine kx minus omega t, equation 1, and second is y2 at point x and t, we have done like this way, x and t is equal to a sine kx minus omega t plus 5. That is second equation. Now, these two waves are moving in the positive x-axis, on the positive x-axis, having the same angular frequency, same wave vector, same wavelength, and same amplitude. Now these two waves are superposed on each other on a straight string. Therefore, from the principle of superposition, the resultant displacement of a wave is from principle of superposition. The resultant displacement is the vector sum of displacement of individual wave. Therefore, y at point xp is equal to y1 xp plus y2 x. Now from equation 1 and 2, we substitute the value of y1 and y2. Therefore, y is equal to a sine kx minus omega t plus, instead of the y2, this a sine kx minus omega t plus phi. Clear this thing? Now a is common. Therefore, remaining part is sine kx minus omega t plus sine kx minus omega t plus phi. Now, from trigonometric function, we are using the equation sine plus sine, 2 sine cos, 2 sine cos. So here we are using this equation, sin c plus sin d is equal to 2 sine c plus d by 2 into cos c minus d by, right? Here we are using this concept of the addition of the sine plus sine. This term is we consider as c and this term as a d. Therefore, we obtain 2a now listen here. Sine c plus d kx minus omega t plus kx minus omega t plus phi upon 2 into cos kx minus omega t minus kx minus minus plus omega t minus phi upon 2. So here the kx, omega t cancel, only the phi is remaining. Therefore, y is equal to 2a into sine kx plus kx, 2 times kx. Here minus omega t, 2 times omega t. 2 is common. Therefore, 2 into kx minus omega t. Like this way, sine 2 common kx minus omega t plus phi by 2. That is the phi upon into cos minus phi by 2. Now we know that cos minus x is equal to cos x. We know that the function trigonometric cos minus theta is equal to cos theta. Therefore, we can add this 2a sine kx minus omega t plus phi by 2 into cos phi by 2. Cos phi by 2. So we can write in that form. Therefore 2a cos phi by 2 into sin kx minus omega t plus phi by 2. There is the resultant displacement of the two harmonic waves are superposed on a state string. That also represents a harmonic wave. For this wave, there is our amplitude. The form of this displacement is same as this. Y is equal to a sin kx minus omega t plus phase. So here kx minus omega t plus pi by 2 is also a progressive harmonic wave. That is our equation number 3. Equation 3 is the resultant displacement of is also a progressive harmonic wave. Progressive harmonic wave. It is also a progressive harmonic wave. This wave is also propagating or the moving in positive x direction. Is moving in positive x direction. Now the frequency, angular frequency, wave vector and wavelength are same as the original wave, but the phase is changed. Phase becomes the half. The angular frequency omega, wave vector k and wavelength are same as original wave. The amplitude is A is equal to 2A cos phi by 2. 2A cos phi by 2. But phase is phi by 2. Now here, the amplitude is A is equal to 2A cos phi by 2. If the initial phase is 0, if phi is equal to 0, the amplitude is A is equal to 2A. That means the amplitude becomes the double. And if the phase phi is equal to pi, if phi is equal to pi, the amplitude is A is equal to 2A cos pi by 2 becomes the 0. Amplitude becomes 0, hence displacement of a point is also 0. Displacement of a point is also 0. Now again, there is very easy but mathematical equation here. Now we consider, we want to obtain the equation of resultant displacement of two progressive harmonic waves on a state string. For that purpose, we consider the two progressive harmonic waves, both moving on x-axis, having the same angular frequency, same angular wave vector, and same wavelength and same amplitude. But the phases, initial phases are different. Suppose the initial phase of a wave represented by y1 xt is 0, and the second wave represented by the y2 xt has the initial phase is phi. Therefore, the equation of the two progressive harmonic waves are y1 xt is equal to a sine kx minus omega t. That represents the first equation with the initial phase 0. Now the second progressive harmonic wave, the displacement is y2 xt is equal to a sine kx minus omega t plus phi. From principle of superposition, the resultant displacement is y xt is equal to y1 xt plus y2 xt. We substitute the value of y1 and y2 here. Therefore, y is equal to a sine kx minus omega t plus y2 is equal to a sine kx minus omega t plus phi. Now, a is taken common from these two equations. Therefore, remaining part is sine kx minus omega t plus sine kx minus omega t plus phi. We know the trigonometric equation sin c plus sin d is equal to 2 sin c plus d by 2 into cos c minus d by 2. Here we consider this kx minus omega t as a c and kx minus omega t plus phi as a d. Therefore, according to this equation, 2a sin kx minus omega t, that means the c plus d, and d is kx minus omega t plus phi by 2 into cos c minus d, kx minus omega t minus this term d. Therefore, minus kx minus minus plus omega t minus phi upon 2. Now here the kx, omega t cancel. Here the kx 2 times, omega t 2 times. So 2 is taken common. Therefore 2a sine 2 is taken common from kx minus omega t and plus phi divided by 2 into here cos minus phi by 2. Now 2a sine kx minus omega t plus phi by 2. Here cos phi by 2, because we know that cos minus theta is equal to cos theta. So we had this equation in that form, y is equal to 2a cos phi by 2 sine kx minus omega t plus phi. That is the resultant displacement of two progressive harmonic waves. Now, equation 3 is the resultant displacement is also a progressive harmonic wave moving in positive x direction. The angular frequency omega, wave vector k, and wavelength are same as original wave, but the phase is pi by 2. The amplitude is a is equal to 2a cos pi by 2. If the phase phi is equal to 0, the amplitude becomes theta bar. That means the amplitude of a oscillation of a point at which the two waves are superposed is the addition of a amplitude of each wave. Therefore, a is equal to 2a. And if the phase is pi, 180 degree phase, the amplitude a is equal to 2a cos pi by 2. A becomes the 0, hence the displacement is also a 0. So that is the mathematical form of the resultant displacement of two progressive harmonic waves superposed further moving in a straight state. Okay.